Sir, Haricharan sir.
Yes.
May I add this, sir?
Yes, you are on. But there is a very, yeah, you can start, but there is a huge noise. Someone is speaking unmuted.
1 minute, sir. I will check. Okay, sir.
Yeah, thanks.
Dear participants, good evening all. It is our pleasure to introduce Sri Haricharan Cherukuri, a distinguished professional in the field of electrical and electronics engineering. Sri Haricharan earned his BE degree from Anna University, Chennai in 2011, followed by an M.Tech in Power Systems from Shastra University, Tanjavur in 2014. He completed his PhD from Vellore Institute of Technology, VIT, Vellore in 2019. After his PhD, he worked as a research associate at the Power Systems and Smart Grid Laboratory in the discipline of electrical engineering at IIT Gandhinagar until 2021. Currently, he is serving as a deputy manager R&D in the electric powertrain division at OP Mobility India Private Limited. His research interests are focused on energy management in grid interactive microgrids, electric springs, demand side management, home energy management, and the application of optimization techniques to power system problems. We are excited to have Sri Haricharan Cherukuri as a resource person for today's session and look forward to gaining valuable insights from his extensive experience in smart grids and electric mobility. Please join me in welcoming Sri Haricharan Cherukuri. Thank you. Sir, please continue, sir.
Yeah, yes, Bruno. Thanks for that introduction. I think I will start sharing my screen. Actually, is my screen visible?
Yes, sir.
Okay. I hope this cursor is also visible. Can someone acknowledge that actually?
Yes, sir.
Okay. Okay, yeah. So to start this session with, what to say? First of all, thank the organizers for giving me this opportunity to speak here. Although I have been working in industry from the past 3 or 4 years after my PhD and postdoc, these kind of opportunities, keep my teaching skills intact is what I feel, and that is the reason I especially wanted to thank you. Puna, can you please mute yourself? There will be an echo. Can you mute your microphone? An echo is coming.
Sir, is it okay, sir?
No, you can put your this thing on mute, no?
Okay.
Whenever it is required, just on. Thank you. Okay. So that is a brief background about. Sorry, not the brief background. That is all about my gratitude for giving me an opportunity to present something in this FDP. So first of all, I wanted to start this session by acknowledging two people who are, of course, important in doing this work, which I will be showing to you. So what actually we did here is we have tried to develop a battery management solution, which is actually capable of controlling this lithium-ion battery packs. So when I was doing my postdoctoral studies at IIT Gandhinagar, I was actually doing this project as an internal project, which was funded by our power systems and smart grid lab, which is currently headed by Professor Naran Penduria. Currently, he has been promoted to professor in the discipline of electrical engineering at IIT Gandhinagar just 2 or 3 days before. I got that information just right now. That is before this presentation. That is the reason I was not able to update his designation here. Sorry for that. And the other person who has played an important role in this work, which I will be showing to you, is Mr. Kuntal Patel. He is actually an extraordinary BTech student, I would say. He was actually a second year student, and he has supported us in doing this activity. His dedication and hard work which he has put in is really extraordinary. And that is the reason I just wanted to acknowledge these two people before I start the presentation or go into the technical details. So, first of all, let us actually see what is this lithium-ion battery pack and why are people so much interested, or I mean, what are the reasons the lithium-ion or the lithium chemistry is getting popular day by day. So the first point, actually, if you see, in the early 90s or in the early 2000s, we used to actually have these lead acid batteries. Even these lead acid batteries, which you can see here, are which is represented here, is actually a kind of battery which people used to use in most of the residences in India, because in the early 2000s and even in late 90s and early 90s, we used to have power cuts at our homes. Maybe today's generation may not be knowing it, but those days, the load shedding was so common that people used to have these which we call as inverters, the UPS, the unlimited power supply. There we used to have these huge batteries. If you look at the size of that battery and the weight of it, actually it used to be very higher. That is the reason actually we used to, for that shape and size, if you just look, not the shape and size, for the power requirement which we used to have at our residences, for example, we used to run a middle class fan and say, for example, a tube light or two tube lights and two fans maximum on this particular UPS systems which used to have those days. That was, the reason behind that was those days actually this lithium ion is not very common, and people used to use these lead acid batteries, which have very specific, very lesser specific energy. Specific energy you can just see here on the y-axis, wherein it is represented in weight.
మనకి వాళ్ళిద్దరికి ఒకటే హ్యాపీగా
So
చక్కెర నిలిపేసి చక్కెర మిల్లి రైస్ నాకు రాగి పిండి తెచ్చుకొని అయితే
sir, HOD triple E, can you please mute your microphone?
అది బెల్లం తాడి బెల్లం వాడతాం అదే
Arun, did you raise your hand? Prashant. So, coming back to this particular topic, it is. I think people are not in a mood to go ahead with the presentation because it is already 8 p.m. I guess. Anyway, so if we just look at this particular lead acid cells or whatever we are having here, so they use it to have a very lesser specific power or the specific energy, which I could say. So this particular specific power or energy is something which used to be very lesser for the lead acid batteries, and that is the reason even to achieve that level of power, which is close to some 200 or 300 watt hour, I would say. The size of the batteries, would be very higher. But now, actually, if you just look at the evolution of the various chemistries in this particular graph, I think the evolution has gone very up in such a way that basically the specific energy and the specific power, if you just plot it on x and y axis, you can see that various chemistries have specific energy and the specific power requirements. So it is actually because of that. It is always required to improve the chemistry of the batteries. Like, for example, if you just look at this nickel cadmium here, so this particular nickel cadmium battery can what to say, can actually have a better the specific power or the specific energy if you just look at this graph. And Better than that, we have other chemistries evolving, and if you just look at this lithium-ion chemistry which we have, this actually has what to say? I mean, a better specific power and the specific energy. If you can just see here, like if the specific power requirement actually comes down, the energy actually the requirement also goes high. And I mean, of course, energy and power are related. If basically, if we have something here, the specific power or something, then if we try to consume more of this power, of course, the energy which you are having may reduce actually. That is what is actually shown in this graph. So if you just look at the current lithium ion chemistry or the lithium ferrophosphate chemistry, which is being used in the electric vehicles or even at the battery energy storage systems of, I mean, at the grid level, this is the reason, the lithium ion actually has a very good specific energy levels. And also, the life cycles actually, the charge and discharge life cycles which we have are extraordinary in these particular I mean, lithium ion chemistry cells, because if you just see here, they have very longer lives. This is actually an average number which you can see, the 300 to 500 cycles is a very lesser one. But if you just look at the electric vehicles which are being used today or which are being sold in the market, have a very good life cycle. Like for example, if you just I mean, just to quote as an example, the Tata Nexon EV which is available in the market today has a guaranteed battery life of 80 years or 100,000 kilometers, which is 1 lakh kilometers. That means if something happens before 80 years or the car has driven 100,000 kilometers, you can actually ask for a replacement of the battery, which means that uh, there is a substantial improvement in the prospects of the battery, which is actually, I mean, a kind of what to say, which is a kind of a good thing, so that the electric vehicles can progress. And the other point which you can see is, the lower self-discharge rates. This self-discharge rate is nothing but if you just put the battery idle for some amount of time, then it will be like what to say, you will have some kind of SOC coming down or the charge coming down. So this actually can be prevented if you are using lithium-ion chemistry. As far as I know, the lithium-ion chemistries actually have a self-discharge rate of 8%, I mean, per month, which is quite good actually. So, and also the better charging and discharging capacity. If you just look at the lithium-ion cells or batteries which are being used, we can actually go for the super fast charging or fast charging, which we call in industry. Whereas, the other chemistries which we used to have earlier, like the lead acid chemistry, it used to be difficult to achieve some kind of what to say, some kind of fast charging or super fast charging. And the cost actually, of course, of lithium ion batteries is less, but actually, sorry, is high. But I would say that this will definitely improve over time, and the cost of these batteries which we are selling will reduce. So now, typically speaking about the battery management system, which we actually have. So these battery management systems, I mean, what is actually a battery management system and why it is being used? Actually, you can just see here. So the first point, what happens is if you just look at the batteries or the cells which we have, like a combination of cells connected in series and parallel is called a battery. This is a 12th class physics which we all studied. And these cells or batteries, if you just look at them, they are, very much, what to say, they're very much independent. You will not have any control circuitry to it, or you will not have anything to control it. Like for example, if you just go and buy a cell from any of the shops or supermarkets which we have in India, which we use for these, AC remotes or even TV remotes. Here, if you just buy a cell, you will get a cell just like that. You will not have any kind of peripherals with it, so that you can just control it. So these particular batteries actually, yeah, what happens is if we don't control them, the charging or discharging, and if you don't monitor the temperatures, currents, and things like that, you will actually have a degradation of the batteries very quickly. That means, the battery degradation will be very faster than as expected if you maintain it well. So these things actually come in if we don't use any kind of a control circuitry or something which does handle the batteries and cells. Okay. So if you just look at the three major functionalities of the batteries which I have written here, it is actually to protect the battery cells from damage. Of course, excessive charging or excessive discharging or higher peak currents may actually damage the cells of the batteries. So in order to reduce that, we can actually in order to reduce that, we can actually use this battery management systems or the BMS which you call, and to prolong the battery life as much as possible. This particular point, if you just look into, this is actually aimed at what to say, limiting the charges and limiting the discharges whenever the temperatures are high or whenever the internal resistance is varied, whenever the state of health is deteriorated. All these things will come into picture here, and to ensure that the battery is ready for use all the times. This is also one more important functionality of the BMS, wherein you have to ensure that the battery is always usable. That means, for example, if we have if you have charged an electric vehicle battery, you cannot say that the temperature has gone up and so you cannot use this vehicle for next 2 hours. That is not going to help out. Yeah, that has to be, in order to ensure that the battery is immediately usable. This battery management system circuits are also extremely important. Now let us actually look at the functions of the BMS actually, which you can, I think, just go through in these slides which I will be presenting to you. If you just look at one of the function of the BMS, which is actually called as the discharge control. Actually, mind you, there is one thing which is, the battery management systems as such, it cannot actually control the current, or it cannot actually control the temperatures, or it cannot control the charges and discharges. The only thing the battery management systems in the battery packs does is that it will actually it will actually communicate to the other devices, either to reduce the current or either to increase the current, or either to turn on the cooling system, or either to do something. But it cannot actually do it on its own. But it has actually a functionality that if something is going very wrong, and if all the other control units, or if any other devices are not working properly, then it can very well isolate the battery pack from the electric vehicles, or from the grid if it is a battery energy storage system. So now if you just look at this particular discharge control, generally what happens is, the cells or batteries which we have are always dependent on the temperature, the working temperature which we got. So if the working temperature is very bad, there is a chance that you may have some kind of cell explosion, or you can have over temperatures or stuff like that. So it is actually always important to maintain the temperature of the battery in between. That is, for example, in most of the lithium-ion cells, they can work extraordinarily well in between a temperature of say -5 degrees to 45 degrees. Some of the cells these days which are coming can go even until 55 degrees. And so if you actually have this particular temperature block, or if you are maintaining the batteries at this particular temperature level, you can actually always say that you are in the safe operating zone. On the other side, voltage is also an important factor. Generally what happens is, you should not overcharge the battery. Say for example, the lithium-ion cells which we have, generally we do not charge them beyond 3.6 or 3.7. Of course, it may sometimes vary. It may even go on to 3.9 or 4.1 also, depending on the mAh internal resistance and the supplier guarantees and stuff like that. But you will have to just look at the the maximum voltage until which you can charge it, and at the same time we have to be careful of over discharging also. That means the voltage across the cell should not go beyond a certain value. Like for example, if you just look at it here in this example, we have shown it as 2 volt. That means any lithium-ion battery packs, whichever we have, the cell actually should not get drained more, and the voltage across the cell should not reduce beyond 2 volt. If it actually reduces beyond 2 volt, sometimes you may have a chance that the cells get dead and you have to replace them. So now considering this voltage on this y-axis and this temperature on the x-axis or the abscissa, so you should be in a position to draw some kind of a safe operating area in green, to say that look, operate these cells in this temperature level and in between this voltage horizon. So it is actually in this particular area you have to operate your cells. Actually, if things are going out of this particular block which I have shown, it is actually treated as a dangerous area, and BMS of course should get alerted on this, and it has to say that I mean, it has to give a warning to the other control units or other discharge units or the charging units not to uh, stress the battery level and reduce their current consumption. And now the same thing is with the current also. So if, for example, if we are operating the lithium ion cells, I mean, at -5 to 45, we will always have some kind of current capping on this actually depends on the mAh capacity of the cell. Like for example, if you are using a cell which has 3000 mAh or something, then which means you cannot draw a peak current more than 3 amperes. So this safe operating area actually is decided based on the voltage, current, and also the temperatures. So this actually is this is done during the discharging and also the charging, but in this particular scenario I have only presented for the discharge control. Now, actually, if you just look at the charging control, so in the charging control, what happens is you have to, of course, operate your battery within a safe operating area, which actually I have shown you here. But the thing is, you have to take care of some additional things also while you are charging the system. So the other things which you have to take care of is actually you should not actually charge the cells beyond their capacity. Like as I told to you, if for example, if we are having a 3000 mAh battery, we cannot actually charge it more than 3000 mAh. That means we cannot pump in power more than 3000 mAh, which once again triggers your voltage level across the cells, and also it what to say, it moves the your cells to a dangerous area wherein there may be a chance of over temperature or overheating or whatever. So and also the current actually also should be within the safer limit, and most important actually the temperature of the bank should be within the thresholds. So if your batteries or if your cells are designed to operate in between -10 degrees to 55 degrees centigrade, for example, we have to ensure that the entire battery pack is actually operated in that region. Like for example, assume because of super fast charging or fast charging, if your temperature is increasing, then the battery management system has to inform the cooling system to pump in the liquid coolant if it is an electric vehicle at a higher liter per minute, and get down the temperature. So this will be the responsibility of the battery management system. And also it has to be ensured that the battery pack is charged to maximum capacity in reasonable time. This means generally what happens is every battery pack actually can be charged, say for example, in 40 minutes and at the same time in 6 hours. So if you can charge a battery pack in 40 minutes, it does not mean that you can do it every time. You will actually have some kind of life cycles. That means the supplier gives you tells you, look, these many cycles you can do fast charging or slow charging. For example, some 5000 or 6000 cycles we can do. Actually, 5000 or 6000 times you can fast charge the batteries what is the supplier gives. Then actually we should not overdo this. Actually, maybe we should not go to 7000 or 7000 or 8000 times of super fast charging, which will endanger the life of the battery. So these are actually the things which you have to take care. And the other functionality of actually BMS is to determine the state of charge. I think this is one of the important. I would say this is one of the most researched area in batteries nowadays. As far as electrical engineering is concerned, because research is going on in batteries on the chemistry side also, but if you just look at the research which is being done on the electrical engineering side, the state of charge determination is something which people are trying to achieve. Generally, what happens is this state of charge is something which you cannot get it readily available from any. From any kind of a sensor or from any kind of a timer circuit. So this is something which we have to estimate. So estimation of the state of charge is always a tricky thing, but there are 3 methods which are being used in the literature currently, and of course there are many other ways people try to do it also. But the point is, if we try to go for more complicated algorithms, like for example using ANN, RNN, or some kind of optimization techniques, or reinforced learning, artificial intelligence, I don't know, whatever. Those things, if you use, the major problem which we see in industry is that as long as you do them on your computer, and if you on a computer and or a PC which has a very higher rating, that is okay, very higher storage capabilities and computational capabilities. But as far as the BMS which is used in the vehicles is concerned, it is actually a simple NXP or a Texas Instruments microcontroller, which has the restrictions on the memory size, or which has the restrictions on the what to say, the run times and stuff like that. So in that scenario, we will not be in a position to use those complicated algorithms which generally run on the computers. But traditionally, even today, if you just look into the SOC estimation algorithms which are being used in electric vehicles, we are trying to use, what to say, this OCV characteristics of the cells and trying to estimate the SOC and stuff like that. Industry still did not go into using the complicated algorithms because of the restrictions in the sizes of the memory which they have. So the first method which generally people use is the voltage determination. So as you are aware that the cells and batteries, the batteries which we have in the market, or which exist in this world, generally try to reduce the terminal voltage whichever is available at its end if there is a discharge. Like for example, at 100% SOC, each cell may have voltage of 4 volt, which will be its maximum voltage. And after that, whenever you start discharging the battery, or then what happens is, the voltage which appears across the cells will come down. This is actually a characteristic of the cell. So now, if your voltage actually is at a higher level, then we can assume that your SOC is also higher. And if the voltage across the cells comes down, then we can say that the SOC has come down. That means the power which you can draw from the battery has come down. But unfortunately, this method sometimes fails because whenever you try to load the battery pack because of load the battery pack because of some transient conditions and stuff like that, the voltage across the cells will momentarily decrease for some time, and it may increase to a certain level after some time. But as long as the load is connected, we will always have a dip in the voltage because of the voltage regulation factors which people are aware of. So this is a drawback of using this method. But as far as the open circuit voltage is concerned, this method actually works very well. The other thing is actually the Coulomb counting. So Coulomb counting, what happens is, if we actually know the initial SOC, so say for example, once if you charge the battery pack to 100% SOC, it means that the voltage appearing across all of your cells will be at say 3.8 or 4 volt. That means that particular initial SOC can be considered as 100% or 95% based on based on the scheduling in the battery which you're doing. So if we consider actually this as 100% of the initial SOC, and from there we can estimate the amount of current which is flowing from the battery pack or during discharging, and during charging what is the amount of current which is flowing into the battery pack. And if this current, if you integrate it over time, then basically you will be in a position to know the area of that particular curve, and that actually you can very well subtract from the initial SOC which you have. But the very problem with this particular method is sometimes this initial SOC estimation itself will become difficult because it is something like we will not be in a position to if for example, if you are not charging the batteries to 100% of its SOC, say for example you are charging it to 60 or 70% of the SOC, then at that time you need to immediately understand what is your initial SOC. If you basically say put this constraint of charging the battery to 100% all the time, it actually may not work out. So this is one thing. And the other thing is this initial SOC estimation depends on your state of health of the battery also. All these things put together, this also poses a challenge. So generally what people try to do is that they try to combine these two methods, the voltage determination, the Coulomb counting, and somehow come to an estimation of the SOC and try to use it. So this is also an important functionality of a BMS. And coming to the other functionality of the BMS, which is the state of health determination. So this state of health determination, or SOH which we call, this is actually a kind of a degradation capacity of the battery, which happens over time. Until now, what people used to do in the battery energy storage systems or BESS level is that they actually consider some kind of annual degradation to be to be at a certain value. Say, for example, if you take these BESS storage, which generally people use for extracting green hydrogen, then people what they do is that they consider a fixed value of 12% in a year, which means they say that if in this year if our battery capacity is 100 kWh, the next year the available battery capacity will only be 88. So like that, actually they depreciate every year, and they try to estimate the state of health. But this is once again a very empirical or analytical technique, I would say. Uh, uh, because we are not trying to determine anything here, we are trying to take a fixed number. Sometimes it may go wrong also. So this is actually one challenging area where researchers working in electrical engineering can actually work on it. But I mean, in order to actually give a hint, if you just look at it, one of the factor on which this state of health estimation depends is on the cell internal resistance of the cell impedance, which is actually written here, or the cell conductance, which I would say. So based on this internal resistance of the impedance, which we cause, I mean, uh, which you can monitor in the cell, we can actually know what is the state of health of the battery. Because as the cell ages, the internal resistance, of course, increases, which reduces the storage capacity of the cells or batteries. Now, coming to another important function of the BMS, which we actually call it as cell balancing. So, this cell balancing is nothing but, as we all are aware, that a group of cells connected in series or parallel only make a battery. And then what generally happens is these particular battery management systems which we have should be in a position to balance the cells. Whenever I say balance the cells, see, for example, if you just take this scenario, this particular charging, I mean, during charging, if you're trying to charge your uh, if you're trying to charge your battery pack, say to a overall value, voltage value of this much, so then what happens is individual cells you have to monitor and see what is the level of voltage which you're having. But unfortunately, what happens is some of the cells, because of different reasons, actually get undercharged, and some of the cells basically can get overcharged because of their internal resistance or their positioning in the cell system, or it depends on the various factors which are sometimes out of control. So here, what we actually tend to do is that if there is a difference in the cell voltages seen, like for example, if you say this is at 3.7 and this is at 3.6 and 3.6 and 3.7, once again 3.6. So here actually what happens is we don't have the uniformity in between the cells actually. This is this actually is some kind of what to say, some kind of a scenario which has to be regulated. Like for example, in this case, I mean, just assume that we have to only charge each cells to a maximum of 3.6 volt. So if you just look at this particular diagram, it has only taken only three cells were charged at 3.6 and all the other cells are at 3.7 volt. This is actually a kind of overcharging some of the cells and undercharging some of the cells. See, this overcharging some of the cells actually is sometimes not good. And what happens is this will in fact deteriorate the life of it. So the thing is, if any cell is overcharged, then of course we have to reduce the level of voltage which is appearing across that cell. And at the same time, sometimes what happens is if any cell is weak, like for example, if it is nearing its failure, then also it will actually take more time to charge, and it will what to say, it will undercharge, or it will uh, I would say it will undercharge, and it will never come to the set 3.6 volt. I mean, what to say, which we are discussing. But yeah, but in this case, it is assumed that this 3.6 volt is reached, after a higher duration. That is the reason some of the cells got charged to 3.7. Okay, so now how do we actually deal with these kind of differences which we have in the cells is by implementing some of the techniques, which out of which the first one is actually called as active cell balancing. This active cell balancing is nothing but if you just look at these cells which are available here, which are connected in series. So what we try to do is that we actually try to connect we actually try to connect actually a switch which you can actually see, I mean, this side. And what we try to do is that we try to close the switch which you have here, and we try to dissipate actually the excess voltage which is, or the excess energy or the excess power which is which this cell is handling to another cell. So this actually can be done using different ways. The one method which you are seeing is by using a flying capacitor method. So what happens is this capacitor will be charged, and after that, this switch which you are seeing here will get closed, and so this capacitor discharges through this particular cell, and it goes on like that. Uh, the uh, the point is that, and if you don't want this cell to be charged, and you just close this switch and also uh, uh, I mean, charge this particular capacitor which is not shown here, and you can actually do like that. So this is, I mean, a kind of balancing which is which can be used. But the drawback of this particular cell balancing is it requires an additional circuitry and also some kind of flying capacitors configurations, which actually is which may be sometimes what to say, which sometimes may be difficult to design and difficult to handle. But the advantage of this is that, I mean, your power, I mean, whatever you are having here in one cell will get transferred to another cell. Okay. And this particular cells, if you just look at here, uh, 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 so you will only have an energy transfer, you will not have any energy loss actually. That is how it works. And now coming to a next way of cell balancing, which you call it as passive cell balancing. This particular passive cell balancing is very simple. It actually has a different cells connected in series, and we will have a resistor, capacitor, and a MOSFET, which will be connected as shown here. So generally, what happens is this cell, if for example, if you think that this cell is overcharged, then you just turn on this MOSFET, and as a consequence, there will be some current flowing into this resistance, and your power will get dissipated here. You will actually not have any kind of what to say, power transfer from one circuit to the other circuit and stuff like that. This is actually one way of doing it, but the implementation circuit for this will be very simple, and also very much cost effective. But the other things which we have to maintain is actually the cooling system also. Like for example, if you are dissipating these cells, and if these resistors are dissipating heat, maybe for some duration of the time, there is a chance that the battery pack temperature will increase. So the cooling system once again has to handle this. If you are trying to do this balancing during what to say, whenever we are whenever the battery pack is idle, then I don't think it will be a problem, because batteries themselves can be cooled in certain time. So the other function of actually the BMS is to establish a communication with the other control units which are available in the vehicle. So what happens here is, of course, if you just look at this particular diagram here, you may actually have some kind of a BMS which comes here. Okay. So this is actually a master controller. So here, this master controller will control all the slaves and of the various battery packs if you have and stuff like that. But this master controller should be in a position to communicate things to the external world and also to the internal world. Of course, to the internal world, we can actually get it done through these slave ICs or the stack board ICs, which we call actually, through some kind of a daisy chain configuration or stuff like that. But this external, communication is also important. For example, if you take this uh, railways, or if you take these automotive vehicles, actually, predominantly this communication from one ECU to the other ECU will actually go on the CAN network, which is called the control area network. And if this PMS has to communicate something to the cooling system or something to another ECU, say for example to this charger which you are seeing here, this actually goes through a CAN communication and stuff like that. So this BMS, if you just look at it, it has to establish an internal communication as well as an external communication. Internal communication is to communicate with its own control boards or its own stack boards or slave ICs, and also the temperature sensors which are available, the current sensors and stuff like that. At the same time, it has to communicate data to the external world, so that the other devices also will be aware of the availability of the power and availability of the charge and stuff like that. Now, if you just look at the different topologies of the BMS, so we actually have three kind of topologies, which I would say: the distributed, modular, and centralized. So these are actually a kind of things which are understandable from here. If you just look at the distributed topology here, what happens is you will actually have one master controller, and this particular master controller controls individual cells or set of cells which are connected in parallel. Like, for example, if you just look at the cells which you are, I mean, which are appearing here, these cells actually are a kind of connected in series. But what happens in the practical applications is that not only cells coming in series, to each of these series connected cells, you will have some kind of parallel cells also, which will be coming here actually. So similarly, generally what happens is in this configuration, if you just see, it is a kind of a 1, 2, 3, 6 series combination, which we call it as 6S cells. And to each of these cells, if you connect another, say for example, 5 cells in parallel, so then we can say it as 6S and 5P combination. So these set of 5 parallel cells can be controlled by one kind of a slave board or an AFE, which we call in automotive industry. So this particular one actually can control this, and similarly will have the connections available to, I mean, to each of these cells. Now this master controller or the BMS communicates it to each of these cells which we have. This actually happens. I mean, using a daisy chain configuration or some kind of a serial communication, to be very basic. So now, whatever has to be controlled or whatever has to be communicated to these cells, generally what happens is we can just communicate it, you know, through this communication line which you are seeing here. So see, I mean, the advantage of this kind of configuration is it is, I mean, highly reliable and simple to implement. But of course, we will have challenges to everything which we do in this world. So people say that mounting can be different, can be difficult and stuff like that. But this is one of the very popular configuration which people use in automotive industry also. I don't know what, I mean, how what people use in BESS and all, but as far as the automotive industry is concerned, this is one of the what to say. This is one of the priority, or what to say, well used topology. Now coming to this modular topology, this is also a kind of what to say, topology to control various parameters of the BMS. But what happens here is we will actually have these cells divided into 2 or 3 sets, and each of the set will have a slave controller, and this slave will individually report to this master controller. I mean, this I think you can understand this simple from this diagram. But the problem of using this configuration is you may need a number of slave controllers like this and one master controller. So the number of I mean, what to say, the number of electronic components which we use actually may increase in this particular topology, and it is actually not used, very predominantly in automotive industry. And also here it is written that one of the advantages is less number of individual PCBs is needed. Of course, this is true, but the electronic components will, of course, I mean, increase, because if you just look at each of this controller, I mean, these two controllers can be mounted in one PCB and stuff like that. But the number of microcontrollers or the AFEs which we use, of course, increase. So now the other one is a centralized topology. So this particular topology is, to be very frank with you, not at all used anywhere practically, because there will only be a single master controller, and this master controller controls each of these cells. This is some kind of a miraculous thing which happens, because if something goes wrong in this master controller, or uh, if there is some glitch which occurs here, then this particular BMS will get doomed. So this is one configuration which people try to avoid. And I mean, the other major challenge is generally what we try to do in automotive industry is that we try to, I mean, we try to use a very simple microcontrollers which actually occupy lesser space and stuff like that. If you use this particular combination, we need a very what to say, I mean, a very robust microcontroller unit or MCU, and it requires a very complex wiring circuitry, because you can see only one master controller or one microcontroller connected to all these things will unnecessarily increase the wiring harness which we call. So we actually, I mean, see, this is the theory part, and we actually, what we did was we tried to implement this on some kind of what to say, some kind of material which we had in the lab. And of course, I am actually thankful to Texas Instruments for giving these ICs, the BQ796068Q1 IC free of cost. They have shipped it from Singapore. When we wrote to them saying that we are we are working on these particular EFEs and we just wanted to know the functionality and we are trying to use this for research work, then they have shipped it free of cost, from another country altogether. So this is nothing but an analog front-end IC, or we call it as a discrete IC. So this analog front-end IC does is that, yeah, I mean, people interested can just note down this particular IC number and they can go to Google and they can search. And if, for example, BQ79606 is not available, you can see for any of these BQ79 series ICs. They are also a kind of AFEs only. What this AFEs does is that they actually have some kind of they actually have an integrated functionality, and this particular, I will show you the the size of this particular chip, which I am showing here. So this actually has a huge, this has a very good potential in handling most of the cells actually, and it can handle variety of functions actually. If you just look here, it can actually monitor the voltage across the cells, monitor the voltage, temperatures, currents, and stuff like that, and also protect them. And this particular AFE also can balance the cell. Of course, here in this particular methodology, or in this particular AFE, only the resistive cell balancing is actually permitted, or the passive cell balancing, as we call it. So, and it of course communicates with the outside world it of course communicates with the outside world, using CAN or UART based on the requirement. So now here what happened was actually during when we are pursuing this particular AFE, as I told you, is eligible, capable of only passive balancing. Then we have tried to implement the passive balancing on it. And if you just look at this particular IC, what happens is this is the AFE which we have. And these MOSFETs and whatever I have been showing to you in the previous diagrams will get embedded in this AFE. The only thing which we have to do is we have to actually only design this particular circuitry in order to achieve the balancing. So of course these resistors which you are seeing here are the bleed resistance which will get connected to this particular, not this resistance, sorry, this resistance connected to this MOSFET. So what happens is whenever we want to reset this cell, if we turn on this MOSFET from another microcontroller, please keep in mind that this AFE is not a microcontroller. It cannot work on its own. We have to give commands to it from another microcontroller. Based on it only this will operate. So if we just look at this resistance which is connected here, if we just try to turn on this MOSFET, this cell actually will get discharged through this REQ, and this is the path in which the current flows. This is an extraordinary IC which I have seen in my life until now, and actually we have some kind of indigenous balancing control also. So indigenous, whenever I say, not something like which is made in India or something. This is what to say. This is inbuilt in this particular AFE. And what actually we did for this MCU selection is that we have actually used the ST microelectronics microcontroller. So why we have used this ST microelectronics microcontroller is that this particular microcontroller can be interfaced with some kind of softwares like YZone or something, and the models which we generally develop on for controlling these things can be directly dumped onto this microcontrollers, wherein we can choose the GPIOs and ADCs, and also decide on which communication has to be used actually. So yeah, this is an application circuit, the snapshot which actually I have taken from the data sheet which you can see here. Again, people who are interested can go go through this data sheet, which is very much self-explanatory. So what we did was we tried to design and printed the PCB with all the peripherals required. And this is actually the 3D view. And the IC which I was telling you, the AFE is only this much. It is a kind of a very small sized IC. with a dual in package. And if you just look at the amount of devices which we have mounted here, I mean the peripherals which you have here are higher than actually the size of the IC and stuff like that. So this is the power of the microelectronics or the VLSI, I would say. But please excuse me for the layout design which you have. We did not make a proper PCB. I am very much aware, but unfortunately at the time we are at the learning stage, so this is what we were able to do. And yeah, this is the final version of the AFE after we have mounted it on a PCB, and these are the resistance and the peripheral circuits which are required. And these are some of the cells which we have purchased. So these are the lithium-ion cells which we have procured, and what happened was these cells are actually 2.6 ampere hour capacity, and the nominal voltage of this is 3.63, and the internal resistance is 0.02 ohm or 20 milliohm. So what happened was when we were actually doing this particular work, we actually got some kind of challenges which we have addressed them later on. So, but those results I have actually not shown here. So what I did was actually we have actually simulated these things in the MATLAB Simulink as well. I will just try to show those results, which are of course same as the ones which we got in real time. So here actually what we did was we have considered the cell balancing. We try to design this cell balancing using MATLAB so that we can implement it in the microcontroller and the AFE which we have. So for this, what we will do is we have selected different battery models which are available in the MATLAB, and these things actually we have designed it very carefully, like the application circuit we have in the Texas Instruments microcontroller. And for this, actually, we have we have designed a control logic as well, which means when these MOSFETs should operate and stuff like that, an enlarged view is given here. So for each of the cells, we have considered something like this, a MOSFET and a resistance and stuff like that. So whenever we want to research this particular cell, what we do is that we try to turn on this MOSFET, and through this resistance which you see, we will actually get it dissipated, and the voltage appearing across this cells will reduce. Yeah, this is one more view of it, and yeah, this is a control logic which we have implemented. Actually, this is if I have to explain each of this block, it will be a little bit tricky, but I can tell you that this is a kind of a state flow diagram which we have implemented. Here, what happens is for each of the cells which we have, so we have tried to implement a state flow wherein we said when these cells should discharge, or in the sense when we will turn on this balancing. This is some kind of if you just ask me in brief what it is, something like when the cell difference between one cell and other cell is so and so volt, the balancing will start. That is a very basic thing which we have considered. Based on it, we have developed this particular logic. So if you just look at the simulation studies which we did, these are some of the details of the pack which we have, and this is the initial SOC and the initial voltage levels we have considered. For example, in the discharging mode, if you can see the voltage levels of each of the cells considered is different, and we try to take a threshold for activation of the cell balancing is 0.03 volt or 30 millivolt. That means if there is a difference of 30 millivolt difference between any two cells, this balancing will activate and reduce the voltage across the particular cell which is at a higher potential. So yeah, these are the voltage measurements. You can see for the first cell it is at 4.15 or 4.2 volt, and later on, because of our cell balancing which we use during the discharge control, the voltage actually got set down at 3.85, and this is for the other cells which you can see. So if you just see at the 1200 seconds of time interval, which means that the voltage actually has come down to 3.85 in the last, and after we started the simulation and when the discharge is on, it means that under 200 200 seconds of the simulation time, the voltage has once again come down. So this is actually how we have done it. And if you just look at the switching patterns of the MOSFETs which we used, this actually works as per the control logic which we have designed. So the first MOSFET, as it has a higher, as that particular cell has a higher amount of voltage, it was turned on during most of all the duration of the simulation. For example, this 2-second MOSFET is also turned on from this duration to this duration, but from here to here, say from 210 seconds to 1200 seconds, it is turned on and off. I'm sorry, I did not have a zoomed image. This is actually, people working in electrical engineering or power electronics will understand that this is not a continuous turning on. Similarly, we have the different switching profiles for each of these cells, and if you just look at the SOC profiles actually during the discharge mode, of course, the SOC of each of these cells is different, but it has been declining, and which means the simulation which we have done is up to the mark. And now during the charging mode also we try to simulate the same behavior of self balancing, the active balancing, and these are some of the results actually which we have obtained. If you can see here, the algorithm, I would say, did not work very well in this duration, because it has actually not made, I mean, it has not allowed this particular cell to get charged, because sometimes if you can see there is a little dip in this voltage. I think this actually can be corrected maybe if we try to improve on the algorithm which we have worked in, which we actually did for the when we did our real-time implementation. So these are the switching profiles during charging mode. If you just look at it, this cell one is turned off from this time to this time, and it is turned on and off in between these things. Yeah. And the SOC profile, if you just look into the SOC profile, also has increased steeply. But if you can see, there are sometimes some kind of coming down here. This is actually because of improper cell balancing which has appeared. And after that, the state estimation worked very well. It has corrected it during the course of time. So yeah, this is what I would like to say. I mean, if you just look at what I have concluded until now, we try to, we try to know what is the balancing and how to implement it, and this is what is written in these two slides. And we have used tools like MATLAB Simulink and stuff like that to do it. Actually, these are some of the references which you can see, which we have taken. Maybe some of them are conference papers, some of them are some kind of journal papers, and some of them are websites actually. Yeah, I think that is all from my side. Thank you. If there are any questions, I will be happy to take. Like anyone? Any questions? Thank you. I think Kalpesh has asked a question. What is delta V? This delta V is nothing but generally what happens whenever we have this. Whenever we want to implement this cell balancing or stuff like that, always what is important is we have to take some base of voltage or some difference in voltage, because see, for example, if we are, I mean, if we are allowed to charge the cells until 4 volt, then we have to actually try to see what is the difference between that 4 volt and that 4 volt actually is the base value of voltage. If you take, for example, so this 4 volt is and the rest of the cell voltage, if you just try to subtract it, then what is the difference in value if you are getting? If the difference in value is 30 millivolt in this case, then that's okay. We need not discharge or something, or else we have to start the cell balancing, is what it means. Did I answer your question? Or sometimes what happens is, instead of taking this reference, we can also take the maximum value of the cell voltage which is appearing in the stack also. See, for example, if you are having 5 cells and one cell is at 4.1 and the other cell is at 3.6, we can actually see the difference between the maximum voltage of the cell which is appearing and the minimum value of the voltage appearing. If it is greater than 30 millivolt or something, then also we can turn on the cell balancing. So this delta we can calculate in two ways. One is by taking an outside reference of the maximum voltage and comparing it with all the other cells, and the second one is taking the maximum voltage which is appearing across the cells in the battery pack itself. I think if you consider maximum value of voltage is appearing across the battery pack, it will be more practical and useful than taking some kind of a constant value from outside the box. Yeah, thank you.
Sir, any questions, sir, from audience side? Okay. Haricharan, sir? Haricharan, sir?
Yes, 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 yes.
I'm audible, sir?
Yes, yes, you. Yes, yes, you are audible.
Okay. Thank you, sir. On behalf of everyone, I extend our sincere thanks for your insightful session on development of lithium-ion battery management systems. Your expertise and clear explanations, coupled with practical examples, greatly enhanced our understanding of this critical technology. We appreciate your time and effort in sharing your knowledge with us and look forward to future session with you. Thank you, sir.
Yeah, thank you very much. Okay, thank you. Bye bye. Good night.
Thank you, sir. Thank you all.